Today we're going to look at a transient mass balance example. So as we talked about in the last video, transient is when we don't have a steady state system. So the concentration is either increasing or decreasing, but it's not at a steady level. And this example is taken from the TU Delft online course in the basics of transport phenomena, and that's quite well done. So I've included a link in the description. So in our situation here, we have a tank, and this tank is full of salt water. It's a 100-liter tank, and the initial concentration of salt is 30 kilograms per cubic meter. We have clean, pure water flowing in at 5 liters per second, and then we also have water flowing out of the tank at 5 liters per second, but that will have some salt concentration, and that's what we're looking to find. So the first part of the question here, number one, what is the salt concentration if t goes to infinity? T goes to infinity, C equals question mark. Well, this is something that we can answer just by thinking about it. So you have salt water in the tank and clean water's continuously pouring in. It's perfectly mixed. In the output, initially we're going to have a high salt concentration that's going to come down and down and down until we eventually hit zero. So at time is infinite, c equals 0, and this is something that we can use to check our answer. 2. Set up salt mass balance. So I like to start the mass balances in really simple terms. So we're going to look at accumulation. In this case, the salt won't be accumulating, it will be depleting, but that will be a negative accumulation. So accumulation equals in minus out. And so we know that there is no salt going in. So in, that's already going to 0. So let's put the accumulation and the out terms into mathematical expressions. So mathematically, the accumulation is going to be the volume of the tank times the change in concentration per time. And that will be equal to the outflow. The out term is negative Q2 times C. So what we can do here is put the C's on one side and the other terms on the other. So we can do dC over C equals negative Q2 dt over V. And then we integrate these. We do the integration and we get that the natural logarithm of C equals negative Q2 over V times time plus an integration constant K. And solving for C equals e to the power of negative Q2 over Vt plus K. And to simplify that, C equals e to the negative Q2 over V times T times e to the K. So we need to find out what our constant is here, and we can use our boundary conditions for that. We know that C at time equals 0 is going to be 30 kilograms per cubic meter. Equals e to the Q2 over Vt times e to the K. Now, when t equals 0, this is going to be e to the power of 0, and that just goes to 1. So 30 kilograms per meter cubed is going to be e to the power of K. So we can rewrite our equation. concentration equals e to the power of k, or 30 kilograms per cubic meter, times e to the power of negative q2 over v times t. This is our mass balance. And we can just look at it to see if it makes sense. Start by looking at the units. We know that the units of concentration are going to be mass per volume. And so here this is the initial concentration, mass per volume, great. So we expect that this part of the term will be dimensionless because we're multiplying by the units that we want, the target units. So let's check. So Q2 is a flow. That's going to be in volume per time. So let's say cubic meters per second. Now we divide that by volume. Okay, the cubic meters are gone. We're left with 1 over second. And we multiply that by time. That leaves us with a dimensionless exponent here. So the units on the left side equal the units on the right side. That's a very good sign. Let's check our other boundary condition. When time approaches infinity, we know that the concentration is going to 0. And so as time approaches infinity, that will give us a very large negative exponent. Now, a very large negative exponent, that's going to 0. So concentration at infinity will equal 0. We're good. Now let's move on to part 3 and solve this balance, find what the concentration is at t equals 20 seconds. So C at t equals 20 seconds equals 30 kilograms per cubic meter times e to the negative 5 liters per second over 100 liters times 20 seconds. Seconds cancel seconds, liters cancel liters. 5 times 20 over 100, so that's e to the power of negative 1 equal 30 kilograms cubic meter times e to the power of negative 1. So we plug that into the calculator, and that gives us 11 kilograms per cubic meter, which of course is just the same as 11 grams per liter. So we started with a concentration of 30 kilograms per cubic meter, and after only 20 seconds, we're down to less than half that. So we can see that the concentration is declining quite quickly. And if we wanted, we could, put this into Excel and find the concentration at every point in time, at every second, and make a graph to see how the concentration goes down over time. And that would be a very effective way of visually modeling this transient situation. So I hope this has been useful to you, and make sure to check in next time. And we'll do something a little bit more complicated, building on this to a mass balance more directly applicable to environmental engineering practice.